Imagine, if you will, being able to rewind time. Not by a year, not by 1,000 years, and not even by 1,000,000. You're hurtling into the past, flying past the age of dinosaurs, past the dawn of life on Earth, past the formation of our solar system. You watch the first stars die out, the first galaxies merge in a furious dance. You race further and further back into a hazy, unfathomable era when nothing we know existed. No planets, no stars, not even atoms. You stop at the mark, 13.8 billion years ago. Before you, a point, infinitely small, infinitely dense, infinitely hot. This is the beginning of everything, the Big Bang. But what happened next? We often talk about stars and galaxies, but what was happening in those very first, most chaotic, and most crucial moments? Let's embark on a journey through the first 100 years of the universe, an era when the fundamental laws of our world were being laid down. The Big Bang is not an explosion in the conventional sense, like a bomb detonating in empty space. It was the birth of space and time themselves. In the very first moment, known as the Planck epoch, the universe was so incredibly tiny that its size was smaller than a proton. And within that volume was contained all the energy of the future cosmos. The conditions were so extreme that our modern laws of physics simply don't apply there. All four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified. It was a single, incomprehensible super ocean of energy. We don't know what came before that moment, and perhaps we never will. It is a wall that our knowledge runs up against. This epoch lasted for only 10 to the negative 43rd seconds. An unimaginably brief instant, yet within it, everything was hidden. And immediately after this unimaginable moment, something incredible happens. The era of inflation begins. The universe suddenly starts expanding at an insane, superluminal speed. It's important to understand, it wasn't matter traveling faster than light, but space itself stretching like a rubber sheet. In a fraction of a second, lasting approximately from 10 to the minus 36th power to 10 to the minus 32nd power of a second, a tiny region smaller than an atom inflated to the size of a grapefruit, or perhaps even larger. This process was akin to the instantaneous inflation of a cosmic balloon. Why was this necessary? Inflation solved several key problems. Firstly, it made the universe incredibly uniform. Imagine wrinkles on a piece of fabric. If you stretch this fabric very tightly, all the wrinkles will smooth out. Similarly, inflation smoothed out the initial inhomogeneities. Secondly, it explains why our universe is so flat in a geometrical sense. And most importantly, it was at this moment that tiny quantum fluctuations, microscopic tremors of energy, were stretched to astronomical sizes. These fluctuations became the seeds from which, hundreds of millions of years later, galaxies and clusters of galaxies would grow. Every star you see in the sky is a distant descendant of such a microscopic ripple in the first moments of time. When inflation ended, its energy gave rise to a colossal number of elementary particles. The universe transformed into a seething, unimaginably hot soup known as quark-gluon plasma. Its temperature reached trillions of degrees. In this soup, quarks, the fundamental building blocks of protons and neutrons, and gluons, the particles that glue them together, floated freely. Also present were leptons, such as electrons and their exotic relatives. It was an epoch of absolute chaos. Particles were born and instantly annihilated, colliding with their antiparticles. Matter and antimatter constantly transformed into one another and into pure energy. Imagine a boiling cauldron where the ingredients aren't merely cooking, but are constantly changing their form, vanishing, and reappearing. In this cauldron, nothing more complex than elementary particles could exist. Any attempt by quarks to combine into protons or neutrons was immediately thwarted by the monstrous temperature and density. The universe was like the inside of a giant particle accelerator, but on the scale of the entire observable cosmos we see today. As the universe continued to expand, it cooled. And then, when it was approximately 1/1,000,000th of a second old, the temperature dropped enough for quarks to finally combine. The strong nuclear force took over. Quarks began to clump together in threes, forming the first protons and neutrons, the particles that make up the nuclei of all atoms. This moment is known as the Hadron Epoch. The word hadron literally means particles made of quarks. Now the soup became a bit more structured. Instead of free quarks, floating in it were protons, neutrons, and other less stable hadrons, which rapidly decayed. But the chaos was still very much present. The density and temperature were still so high that protons and neutrons were constantly colliding with each other and with other particles. It was at this very moment, in the first second of the universe's life, that a great battle unfolded: matter versus antimatter. According to our theories, when particles were born from energy, an equal amount of matter and its mirror image, antimatter, should have emerged. When a particle meets an antiparticle, they annihilate, transforming into pure energy, a flash of light, gamma-ray photons. If their numbers had been precisely even, then after the universe cooled, they would have all annihilated each other, leaving behind nothing but an ocean of photons. There would be no stars, no planets, no us. But by some fortunate accident, for every billion particle-antiparticle pairs, there was one extra particle of matter. This tiny asymmetry, just 1 in a billion, is the reason our world exists. Billions of particles and antiparticles annihilated in a giant flash, while that very tiny excess of matter remained. All the matter that makes up galaxies, stars, and you and me is the residue from that great battle. Why this asymmetry arose is one of the greatest mysteries of modern physics. When the universe was 1 second old, the temperature had dropped to approximately 10 billion degrees. The annihilation of matter and antimatter had largely concluded. The universe now consisted of protons, neutrons, electrons, neutrinos, and a vast number of photons, particles of light born during the annihilation process. This ocean of light was so dense that it made the universe utterly opaque. A photon could not travel even a millimeter without colliding with an electron. But the most significant event was still to come. In the interval between the first second and roughly the third minute, the temperature plummeted to 1 billion degrees. This was a magical threshold. At such a temperature, protons and neutrons, upon colliding, could no longer merely bounce off each other, but instead merge, forming the very first atomic nuclei. Primordial nucleosynthesis had commenced. Imagine a cosmic kitchen where, in just a few minutes, the universe's fundamental chemical composition was cooked up. Protons, which are essentially hydrogen nuclei, began fusing with neutrons, forming deuterium, or heavy hydrogen. Then, deuterium nuclei captured more protons and neutrons, transforming into helium-3 and helium-4 nuclei. As a result of this short but turbulent process, almost all free neutrons were packaged into highly stable helium-4 nuclei. By the end of the third minute, primordial nucleosynthesis was complete. The universe had cooled enough for nuclear reactions to cease. So, what was the final result? Approximately 75% of all ordinary matter by mass remained in the form of protons, that is, hydrogen nuclei. The remaining 25% had been converted into helium nuclei. There were also tiny traces of deuterium, lithium, and beryllium, but their amounts were negligible. This composition, 3/4 hydrogen and 1/4 helium, predicted by the Big Bang Theory, perfectly matches what astronomers observe today in the oldest stars and distant gas clouds. This is one of the strongest pieces of evidence that our theory is correct. The universe received its basic factory firmware, its initial chemical composition, in just 3 minutes. Following the end of nucleosynthesis, a long and relatively calm epoch ensued. For the next several tens of thousands of years, the universe was a hot, dense plasma. Within it floated hydrogen and helium nuclei, along with free electrons. And all of this was bathed in the dazzling light of photons. As we've mentioned before, due to the free electrons constantly scattering light, this plasma was completely opaque. If you could have been there, you would have seen nothing but a bright, uniform white veil in all directions, much like an extremely thick fog or what lies inside the sun. The temperature slowly dropped as space expanded, and although, at first glance, nothing was happening within this uniform fog, in reality it was precisely during this time that the primary invisible force, dark matter, began its work. Dark matter is a mysterious substance that does not interact with light. We cannot see it, but we know it exists due to its gravitational influence on stars and galaxies. There is approximately 5 times more of it than there is of ordinary, visible matter. And during the plasma epoch, it had a tremendous advantage. While ordinary matter, protons, helium nuclei, electrons, was constantly subjected to pressure from photons, which prevented it from collapsing under gravity, dark matter was immune to this pressure. Photons simply passed right through it. Consequently, while ordinary matter remained uniformly distributed throughout the plasma, dark matter began to slowly but surely clump together under its own gravity. It formed invisible gravitational wells, or halos as they are called. These dark matter halos became an invisible framework upon which ordinary matter would eventually accrete. They were the seeds of future galaxies. Without dark matter, the gravity of ordinary matter would have been too weak to form large structures like galaxies within the lifetime of the universe. And this is where things get really interesting. Ordinary matter, even though it couldn't yet fall into these gravitational wells due to light pressure, still felt their pull. A grand tug-of-war ensued. Dark matter's gravity pulled ordinary matter inward towards the clumps, while the pressure from hot photons pushed it outward. This standoff gave rise to giant waves that rippled across the entire universe. These were sound waves, or, to use the scientific term, baryon acoustic oscillations. Yes, the early universe had its own sound. Of course, this wasn't a sound we could hear, but rather waves of density and pressure in the plasma, propagating at a speed exceeding half the speed of light. These waves, like ripples on a pond, spread out from the initial density enhancements. They compressed and rarefied the plasma, creating a distinct pattern in the distribution of matter. These sound waves traveled throughout the universe for hundreds of thousands of years, as long as it remained opaque, and they left behind a trace that we can still observe today. This trace is visible both in the cosmic microwave background radiation and in how galaxies are distributed in space. By measuring the characteristic size of these ripples on a pond, we can very precisely determine the parameters of our universe. So, let's recap what the universe was like at the age of 100 years old. It was still a gigantic, expanding ball of hot, opaque plasma. The temperature had dropped from trillions of degrees to a few 100,000 degrees, still incredibly hot by our standards. Floating within this plasma were hydrogen and helium nuclei, as well as free electrons. The universe's energy was primarily concentrated in photons, particles of light. There were far more of them than particles of matter. That's why this era is often called radiation-dominated. The cosmos was flooded with brilliant light, but this light was trapped within the plasma, unable to travel freely. Somewhere within this plasma, invisible and imperceptible to light, clumps of dark matter were already forming and growing. They were creating the gravitational landscape of the future universe, valleys and hills that would determine where the first stars and galaxies would appear. And throughout this plasma, echoes of cosmic sound, gigantic density waves, were rippling. For the universe's 100th anniversary, there were no fireworks. There were no cakes and candles. It was still the same era of waiting. The main ingredient, hydrogen and helium nuclei, was ready. The invisible framework of dark matter was rapidly taking shape, but for the next step, the creation of atoms, the universe needed to cool down even further. Electrons were still too energetic to stick to atomic nuclei and form neutral atoms. They zipped around the plasma like balls in a pinball machine, constantly knocking photons of light off course. The universe awaited its great enlightenment. This event, known as recombination, would happen much later, when the universe was approximately 380,000 years old. It was then that the temperature would drop to 3,000 degrees, and electrons would finally be able to combine with nuclei. The plasma would become a neutral gas, and the universe, for the first time in its history, would become transparent. The light that had been trapped within it would break free and embark on an eternal journey. It is this very light we now capture with our telescopes as cosmic microwave background radiation, or relic radiation, the most ancient echo of the Big Bang. Yet, that moment was still a very, very long way off. The first 100 years marked an epoch of fundamental physics unfolding across cosmic scales, an era when the universe evolved from a singularity into a superheated soup of elementary particles, then a plasma of the first atomic nuclei. It was during this time that the key parameters of our world were defined: the total amount of matter, its fundamental chemical composition, and the very seeds for future cosmic structures were sown. It was a time of profound silence, save for the resonant hum of sound waves within the plasma. A time of impenetrable darkness, if we consider the possibility of seeing anything at all across distances. Yet, it was far from a dormant age. Instead, it was an epoch of hidden, titanic labor. Though we might only envision a boiling fog, beneath its shroud, gravity had already commenced its slow yet relentless task of constructing the world we now inhabit. Every single atom you possess, hydrogen, carbon, oxygen, passed through that fiery cradle. The very hydrogen nuclei in the water you drink were forged in the first second of the universe's existence. They traversed that plasma, becoming an integral part of those very sound waves. The story of each of us begins not with our birth on planet Earth, but rather there, amidst that primordial fire during the first 100 years following the dawn of time. This is our oldest legacy, etched into the very fabric of creation itself.